Yeah, okay. Oh, thank you, Thibaut. Thank you for this opportunity to talk this morning. What I'd like to do is to give you an introduction to what some of the work that we do in industrial science. I'd like to talk about a few projects that me and my colleagues have been working on in some different areas, just to give you a feel for the kind of things we do and why we do them. But first of all, I'd like to just give you a very brief introduction to Cargill, as they as they pay my salary. Um, we're a very big company, but a family-owned company, so we're not listed on any stock exchanges. So perhaps you haven't heard of us. But there are about 160,000 employees in 70 countries, and so a very large global company that's been going for about 160 years. And what do we do? Well, these are the areas that Cargill works in. So started off as a company that was buying grain from the farmer, processing it and selling it, so in the agricultural supply chain. And then you move out from that into what can you make from this grain? Well, animal nutrition, so you can make animal food, so you move into animal nutrition, animal health. Then you can start to think about the animals. So you can start to think of things like beef, chicken, turkey, and so you have the protein, animal protein business, and also a salt business, which is put in with that. We're owning salt mines, but also sea salt around the world. And then, of course, with the agricultural supply chain, you can do the raw processing, but you can start to improve it, make cleaner ingredients that are easier to use in foods. So we could start to think of things like refined oils, cocoa, chocolate, emulsifiers, texturizers, the rest of it. So we have the food and bio space. And then, of course, we can also, as well as using them in foods, we can look at putting them in things like beauty products or in the industrial space, particularly to replace petroleum-based products. And then, of course, within the agricultural supply chain, there's a lot of trading and financial services that can be provided. Companies want to hedge, farmers want to guarantee prices. So you've got some kind of banking financial services divisions. So this is effectively what Cargill does. And so we're a B2B business in the main. So we help our customers win. So we help our customers to have high quality products that they can use and that they can sell. And so we can see, delivering breakthrough innovation by research and development, having good intellectual property, sustainable solutions, and strategic alliances. So working together with our customers, with suppliers, is very important. You just get an idea of all the different ways in which Cargill works. And so where is Cargill? Well, this is where our employees are. So you might think only 14% in Europe, the Middle East and Africa, but of course 14% of 160,000 is still quite a lot of people, I guess. 20,000 or so, yeah. And so you can see that there is a significant amount of investment in Europe. And of course, Cargill was a North American company, so a lot of people are in North America and Asia Pacific. Well, the markets are growing. Particularly with the growth of China and Indonesia and places in recent times. So there's a lot of investment in Asia Pacific and a big growth there. But let's think about that. So that's just an introduction to Cargill. But let's think about food industry R&D. So what are the critical questions that industry and industry scientists need to solve? And we can think of this in two ways, both from the company perspective, but first of all from society perspective. What are the kind of issues that the world is dealing with? Because companies are going to have to deal with these as well. And so if we want to have thriving companies, thriving societies in the future, these are the things that will need to be answered. So, resource competition. How can we balance increasing food demand with limited resources, such as land, water, and energy? How can we reduce food waste across all stages of the supply chain? and how can we provide food to what's becoming a more and more increasingly aging population. Then we can look at human rights and environmental impact. What strategies can we have to minimize the potential impact of food production? I mean, we can look at agriculture, particularly sort of cows or cattle, and cattle are a very significant contributor to methane production, which is an important greenhouse gas. How can we stop that? And so there are products on the market, to put in animal feed, which can reduce the amount of methane cows produce. So little things like that. And then, how can we prevent forced child labour in the supply chain? How can we ensure everyone has access to adequate and nutritious food, regardless of economic status or geographical location? I mean, I think you can say that, look, in a fairly advanced society, that there shouldn't be anybody going hungry. So if people are going hungry, that's a fault of the political and economic system in that country. And how are changing diets and consumer preferences influencing food production and distribution? So what are the changes that are happening? How can we help manage these changes? So these are all sort of societal questions. But then we can also look at it and say, what do we want to do from industry? I think what we want to do is find ways to produce nutritious food in a low-cost and sustainable way. So we want efficient processing, and we want minimal processing, minimal resource use. How can we remove chemical treatments, replace them with more sustainable, friendly processing or bioprocessing? And get rid of acetone, hexane, and things from all the processes. Sustainability is important. Nutrition. How can we improve nutrition for the world? How can we make nutritious, low-cost, nutritious products? But then, of course, I think a big one for industry is how can we generate added value in our products? So how can we make products that have the value that our customers want to pay for, so that we can make money, and then we can justify having more research and development to make more products. But of course, the bottom line is always profit. So there's no point doing anything if we don't make profit. So we have to think about how we're using our research to generate profit. And then, of course, that there's we think this is all about research, but what we want is innovation. So we want new innovations, new products, new processes that are going to provide benefit, to the consumer at the end of the day. And so, do we always need cutting-edge science? Well, I think one good example, perhaps, is the Viennetta. It's maybe a bit old-fashioned now, but the Viennetta product, ice cream with a bit of chocolate, so it's a bit crispy and everything. And it was in the Unilever made lots and lots of money, I guess, from this. I mean, it was a big seller in the sort of 80s, 90s, 2000s. But how was this invented? Anyone got any ideas? It was by the operator on the line. It was just playing around with the nozzles at the end of the line and started to play around. So got these nice structures, and they looked at them, thought that they were interesting textures, and then they did some work and developed some IP, and it came from there. So we don't necessarily need the high quality science, but our research should be leading towards innovation. So I think that's a good example of something. Innovation, ideas come from everyone in the business. So what I'd like to do, for the most part of my talk, is just to give you, I think I've got 4 examples of different areas we've been working on in our team within Cargill, and just look at some of the issues, some of the science that we've done, and give you that introduction. So I think the first thing we can look at is removing trans fat from products. So hydrogenation was a process that was invented back in 1901 to harden vegetable oil. So the idea is, yeah, you can't make, if you take olive oil or sunflower oil, it's all liquid. You can't make margarine or anything from it. You need to make a hard fat. So you react it with hydrogen, and you get trans unsaturated fats instead of the cis unsaturated fats, and these are solid. And so you can do things with them. You can make nice things with them. From a functionality perspective, they're fantastic. They're easy to work with. You can make lots of nice things. You get nice crystals, get nice plastic crystals. So they're great, but they're bad for your heart. And so you can look at the number of deaths that have happened from the trans fats in the diet. So Cargill has taken a lead on this and decided to eliminate trans fats from our portfolio. So we're not making trans fats anymore, and this means that customers need to adapt. Now, if you've been living in a Western country, you'll have seen over the past 10 to 15 years that they've disappeared. But because they are relatively cheap in certain countries, that they have still been used in the diet. And if we look at trans fats, you can see what people thought, because they were unsaturated fats, they were healthy. And so even in the 1990s, you can see various articles, claiming that they're more healthy than butter, because butter's full of saturated fat. And even in 2005, in Bailey's Industrial Oils and Fats, which is the kind of Bible of oils and fats, we can see that Walter E. Farr said there will always be a need for hydrogenated fats to provide functionality and improve stability. And hydrogenation is the only way to produce commodity-priced hardened oils. Any alternatives are going to have higher capital and operating costs. So we can see, even only less than 20 years ago, people were still thinking that they were there forever. But of course, that's been all changed. So why would anyone want to use them? They have a high melting point, so that's important where solid fats are important. So we're going to look at some examples in baking in a minute. They have higher oxidative stability, so if you want to fry, the frying oil you're using is not going to go off so quickly, and they have good melting characteristics. They melt in the mouth nicely, and so so they are easy to use. But as of January this year, we became the first global supplier. We said that there is no trans in our supply chain. We will not make trans or supply trans oils to anybody. But of course, that makes it difficult for some of our customers who then have to change their formulations and change the way they're working. So we've worked with the International Food and Beverage Association to produce a manual to help them switch. And we will provide, support and training to manufacturers and associations, irrespective of whether they are Cargill customers. So I've taken part in webinars with different associations around the world to talk about how to change from trans fats. So it's an important change. And here we can see a nice piece of shortening, and so this is why it's going to be important to have the right fat with the right structure. So Alex earlier was talking about the right crystals we need to give us the functionality, and here you see we need to have quite an elastic shortening so that it can be rolled out like this. And if you think of something like the vol au vents or a croissant or puff pastry, then we need it to be able to deform. So we need to have fats which are elastic so they can deform, so we can get the nice air bubbles that we want in the system. If we're thinking of other products, like a cake, then perhaps we just need the fat in the system. It's not so important to have the plasticity, and so we can use a cheaper fat which won't roll out like this. So bakery, it's necessary for the fat, to deform and behave in a specific way. And this gives us the opportunity we want to give you the nice texture you get from a croissant or something similar. So industrially, people have been using trans fats for this. Probably don't want to go back to using things like butter or lard because they're animal fats, and we're looking for plant-based solutions. So how can we do it? Well, in order to do this, we have to take a material science approach to the whole baking process. We've got to look at the whole process and see what happens through the process, see what the fat does, how it interacts with the other ingredients, initially, then through the dough and through the baking, and then that can give us a product with the right functionality. So there's various techniques we have to use, a lot of rheology, texture analysis, tomography, in order to see what's happening at all the stages and try to sort of replicate what's happening with the trans products. And we can see a very simple example of what happens if we look at solid versus liquid, solid fat versus liquid oil when we're baking bread. And so we can see if we just have oil, we don't get, we get a low volume, and the more, if we don't have any oil or fat, we get very low volume. If we just have oil, we get a low volume, but as we increase the amount of solid fat, then the volume of our loaf increases, and we get a nice open loaf, which is what we want. So we can see just adding solid fat into a system's good. Now I don't want to go, can't go into this too much, but so this is what we did. We took a system. In this case, we took the system of pie crust, and we looked at modeling, how we could get systems which would replace the systems used in pie crust. Now, the gold standard for pie crust is lard, and that's the traditional system, certainly in Europe and North America, or Northern Europe and North America for making pie crust. And we baked pie crust on our rheometer. We did various other things, and we found these 3 parameters that we could model, and then we can see there's this sort of region of operability. And if we have a system where we fit in this region, we can get something that works. So what we're able to do, we're able to work with our customers to take their system, to take their fats, and to find a system where we're close in with their system, and then find something that works. So we can use, rheological and other techniques in order to do this. Now, that takes us a certain way along the line. But what we also wanted to do is to measure product performance, measure the quality of our products, and we saw some good work by Alex's team, where they were looking at large amplitude rheology, so Laos, in order to look at the elasticity and plasticity of shortenings. Now, of course, we want to make a shortening. You saw the shortening, the piece of dough that was rolled out earlier on, and we want to make shortenings that work and have good functionality. So we took this work, and Alex's colleague came to visit us, and we took this work, and we looked to apply it to our systems. And so here we can see, so we had these systems from our plant in Istanbul. And what they say is, that they have some good batches and some bad batches, but they weren't quite sure how to differentiate between the good and the bad batches. So what they do is they make a shortening, they leave it in their storeroom for 4 or 5 days, and then they get the baker to test it. And if it's good, then they'll sell it, and if it's not good, they'll rework it. So obviously that's quite an expensive process, that they're wasting time and everything. But we saw with the tools that we were able to develop based on Laos, that we could quite quickly differentiate between good systems which behave in the elastic way we want, and then bad batches which behave in a different way, and then based upon looking at what's happening in the plant at these times, because it's very hot in Istanbul, so it's hard to cool properly. So we can understand why some systems are good and some systems are bad. So I think we can see that by using sort of rheological techniques and rheological parameters, we can get a good understanding of the behavior of our fats, and we can use that to transform them, so we can get the good quality fats that we need without using the trans fats, which clearly nobody wants. So next we'll come on. So we've talked about health. The next thing we'll come on to look at is reducing waste, and I'd like to talk about some natural structuring. So, when a plant is processed, there are lots and lots of product streams. So we could think of something like soya, for example. So you can get, we can get soy oil, we can get soy protein, and that's a certain amount of it. But we can also, there are also other parts of the plant. Now, we don't throw anything away in the processing industry, that there's no waste as such. What we do is to try and get these streams into as valuable systems as we can. But it may be that certain streams, like the plant cell walls, that they're often just used for animal feed. But perhaps there are better things we can do. One thing we can think about is, if you're thinking of something like a mayonnaise or a vegan, well, particularly a vegan mayonnaise. So it might have chemically produced textures or stabilizers in there in order to make the emulsion. But that's not ideal, is it? We don't want to eat lots of chemicals. We'd rather eat plants. So can we find natural systems that will work? And so what we thought, the plant cell walls are a relatively low value stream, but they contain lots of interesting material that we can use and we can functionalize. So the plant cell wall, what is it? It's the complex polysaccharide network that encases the plant cells, and it's got a lot of cellulose and other things. So there's lots of different things. Of course, it varies from plant to plant, but these things have structures, so we can play with these structures and we can do interesting things. And of course, what we can do with those structures depends upon the plant that we take, and this is what things are used for today, without looking at the functionalization of the cell walls. So we can see we talked about soy. We've got soybean hulls, soy flour, meal, gums, soap stock, distillate, glycerol, and bleaching clays. So there's lots of things we already use, but can we make something which is higher value? And we can see, based on the different compositions of the different plant cell walls, there are different applications for the different ones. And so look, what can be the functionality? What can we do with them in food? Well, what we can think about is we can think about things in different ways. So we can think about the technical functions, texturize, thickening, gel, stabilize kind of things. We can think of the sensory, because if we can make something thicker, then it'll affect the sensory, will affect the mouthfeel. That we can think of the health and wellness. So if we can make a nice structure, then perhaps we don't need as much fat in there or something. So we can look at caloric reduction. The fiber can be nutritious, so we can look at increasing the fiber content, and we can have a clean label, so we don't have the chemicals in our product. We can also think, well, these are plant cell wall materials, that they're not necessarily so expensive. So perhaps we can replace things that cost money to make, egg products, dairy products, or expensive gums that might be used to texturize something. So yes, so maybe we can help to reduce and control the cost of a product. And we can see just here, the compositional diversity of the gels. So we can see, for example, in sunflower hulls, you've got, and soybean hulls, you've got a lot of cellulose, where when it comes to wheat bran, we haven't got so much. So we can look at different, different plants, and we can get different things from them, and so that there are lots of different products that are available or that we can use. So what are the options? Well, we can just get a plant. What are the simplest thing we can do? Do nothing. Yes, cheap. If it works, it's good. So just use the plant cell wall as it is. Then perhaps we can, just improve it, make things a little bit smarter, just think a little bit better, improve things to improve the design of an existing process. Then option C, well perhaps we can look at the architecture of the fibers. Perhaps we can manipulate and control that a bit, so we can build something up. Or perhaps even more complicated, then we can take the polysaccharides and build them up in a multi-component, multidisciplinary way, and use this route to provide high-tech solutions. So really push the material science we can get from a plant cell wall. So we'll have a look at the different options and some different results we can get with them, and just to give you an idea. So our approach, so what do we have them? What do we use them for? Well, there's bulking agents. So we can take, the sugar. If we think of something like a biscuit, cookie, we want to perhaps reduce the calories in there, so we want to reduce the sugar. But you can't just take the sugar out, you've got to put something back in. So perhaps we can use as a bulking agent, and perhaps the sugar does something. And so perhaps we can replace the functionality. We can have fibers that have a technical function, so that act as emulsifiers or provide texture, which we can then use, to manage the water, or form some kind of gel or gum or something, but not necessarily a nutritional benefit, just to provide the structure. And then, of course, we see about the fibers in food. So fibers can add a nutritional benefit, and that's something that we could claim. So perhaps someone making a product with a fiber can talk about digestive health, prebiotics, or probiotics, all these kind of things, and they can put a specific claim on their product that it does this, and that could be that could be valuable. So we'll look at the sort of valorization space. We'll look at the level of valorization, and we'll go from bulking, nutritional, and functional. And the first thing is, of course, just use them as they are. So you can see, they just get the cell wall that comes out of the process. It'll swell a bit. It'll give you a little bit of texture. But maybe, in order to get something good, something that works, you'll need to have relatively high inclusion levels. But maybe, you can put it in and you can get some calorie reduction, or you can claim some fiber enrichment. So there is potential, and of course this is going to be a relatively low cost thing, but it's a relatively low cost, but a little research, But perhaps then the next thing, can we do something, just a little thing to it? So perhaps what we can do is just mill the fibers, and we can try and mill them in specific ways. So there's two options, isn't there? We can either try and mill them to get into cellular failure, so we get surfaces that are the plant cell walls, or we can try and mill across, so we get intracellular failure. And here, we've got open cells, and the propagation of the fracture across the cells. So perhaps that gives us different properties. So here, yes. So here, this is what we do. So take the raw material, we mill it, and sieve it, and we can get particles of different sizes. We can look at the morphology with SEM, light microscopy. We can measure the contents. We can measure the moisture. And so let's see what we can do with it. And here we can see some, I don't come out so well, some results. So we can get more, yes. So the small fraction we get can contain cellulose, lignin, ash, insoluble fibers, and hemicellulose. And we can see we've got sunflower, wheat bran, citrus peels, soybean hull, and cocoa shells. So we can see different. It hasn't come out so well, I'm sorry. We can see different, different compositions based upon the different plants that we use. So we can see different functionalities. And we can see, we can get these different morphologies. So we get different, depending how we mill it, we get different structures. And so they're going to behave in a different way. No need to go into it too specifically, I don't think, but I think you can imagine, the differences in the structure, will build up. These will be the building blocks of our final structure. So if we change the shape, they'll be different. And by cutting and hammer milling, we can get the lignocellulosic material will tend to separate into different layers, and then brittle tissues will remain large, whereas the softer ones will be ground up to smaller particles. So we can build up different structures like this. And then, so that's looking at that was looking at the intercellular failure. Now we can look at intracellular failure. Well, we're doing this, so we're going to break open the cells, and by doing this, we're going to get access to things that are inside the cell. So what's inside the corn kernel, for example. And so here we've done a lot of work looking at corn bran. So it's a product you obtain when we dry mill corn. And so it's a source of dietary fiber, contains a lot of phytochemicals, such as phenolic acids and phytosterols. These give us good benefits. And so by this milling, we're able to improve the bioaccessibility of these bioactive compounds. And so, yes, so this gives us healthier food that we can make claims about. And so then we can look at the impact of the plant cell wall dietary fibers on the gut homeostasis and on human health. So we're able to develop micro-milled corn fiber, and we've done work together with our nutritional colleagues and with external partners, and we can show that our products have impact on nutritional health. So it is possible to make claims based upon our products. And so by this milling, you see we're able to get the bulking. We're able to get bulking, perhaps more functional bulking than we could just by using it on its own, but we're also able to get good nutritional benefits. And so, again, this is something which is very important. And now, as we're by the seaside, let's look at some seaweed. So, Cargill has quite a large business manufacturing carrageenan. So carrageenan is about 60 to 80% of the cell wall, and about 20% is other natural materials. You can see glucomannan, sulfated glucan, and cellulose. So, can we use that? Do we need to extract the carrageenan, or can we just use the whole thing? So we have this product called Wave Pure, and this is basically the seaweed flour. So it's the cell walls from the seaweed. So we don't use any hard chemicals or process modifications or non-degradable steps. And so the natural components of the seaweed are kept intact. And so we have this natural structuring material which functions well. It'll gel, form similar kind of systems to carrageenan, and it's made with a much less processing. And this is Wave Pure. And it has lots of applications where you could expect, texturizers to be used. So in the sort of desserts that are very popular in France, ice creams, protein drinks, cheeses, all these kind of things where we want to create a gel or a gummy kind of structure, then we can use this Wave Pure. So you can see here, by understanding the behavior of the seaweed, by processing it gently, we were able to make plant cell walls that fit in this space. So we can create these functional kind of low processed or minimally processed systems. And then finally, option D, well, what can we do? How can we improve? How can we increase the value just of this kind of systems? Well, we can start to think about what we can do to modify the systems. So we don't want to use chemicals, of course. We don't want chemically processed food. But fermentation is a natural process that we see in a lot of foods. So can we ferment the foods, provide nutrients, put some good bugs in, and ferment these ingredients. So we're clearly using food-safe cultures, using food substrates, and seeing what happens. And so by doing this, we're able to create systems, fermented ingredients that can be used in a wide variety of spaces through alternative with different substrates. So the approach is to is to ferment them, and then to ferment in small things if they're successful, to ferment in bigger and bigger things, and then finally to take it, ferment at a large scale, and then give it to the customer to taste. So it's a long process, from a very small scale, looking at different strains, seeing what sort of products come out, gradually screening, and then taking it bigger and bigger. And then at this stage, we're working on internal sort of formulation and understanding the material science, and putting it into products, looking at sensory testing. And then if this is successful, we can make it on a big scale and discuss it with our customers. So here we can see some examples. We can see an indulgent vegan dessert fermented by good bacteria, rich texture, glossy appearance, and perfect balance of sweetness with refreshing acidity. I mean, that's probably written by a marketing person, but it probably, you can imagine what kind of product. Yes, some yogurty type product you can see, and so we can get different formulations, and we can play around with the sensory. But they're clean label. It's simple. It's natural, and it's cultured. It's made by a traditional fermentation process. We're not using additives. We're not using fat, so it's going to be low calorie. It's going to be clean label, and it's got a good flavor. No, I don't. Sorry. But it's a bit of a good product. I'm sure it'll be. Yeah. Sorry. Yeah. It's bacteria in this case, I think. Sorry, I've gone the wrong way. Yeast. Is it? Well, yeast and bacteria we use. Yeah, I don't know which this specific one is. And so here you see, yes, so here you see we're looking at increasing the value, but it's not just the material science that's at play here. We've got the marketing telling you what a delightful product it is. Clearly there's a lot of work on the fermentation, and then there's a lot of work on the product development. So innovation is a teamwork event. It's not just using one specific science and pushing it as hard as you can. I think that's the important message from that. So yeah, to conclude, the plant cell walls, they're very interesting ingredients. There's a big variety in composition. And we can better valorize the agricultural stream, so we can reduce waste. They're potentially very versatile raw materials for different purposes. But then we've also got to think, when you're thinking of a plant, are there contaminants in there? Particularly if you're looking at the outer area of a plant, it could have had pesticides, or something. So we've got to be careful, of course. And what's the regulatory status? And are there lots of plants are green? Are there lots of colour? Is there lots of green in there? Perhaps that's not what we want in a food product, or lots of different flavours that come through from the plant. So we don't want our plant, to taste of raw, our products taste of raw soya, for example. And these kind of things can be important. Okay, so that was the plants, and now I think we can plant cell walls. Now we can move on to chocolate. Of course, I'm sure you all know the best chocolate in the world comes from Belgium, and that's why we're particularly interested in working on chocolate. So what is chocolate? I think it's important, just to cover what chocolate is. It's a product, this is the chocolate directive of the European Union. Chocolate is a product from cocoa butter and sugars, and it contains not less than 35% dry cocoa solids, including not less than 18% cocoa butter, and not less than 14% of non-fat cocoa solids. So this is just limiting the amounts, and it's a composite material. So we've got an internal phase of cocoa particles, sugar, and with the milk chocolate, milk particles, and then a continuous phase of cocoa butter, maybe milk fat. So that's what it is. Now what we need to remember is that cocoa butter is expensive, cocoa particles and sugar are cheap. So what we'd like to do is to put more cocoa particles into the system, more sugar into the system perhaps. And of course, if you put more sugar into the system, what happens to the chocolate? It becomes lower calorie, so it's a more healthy option. So cheaper chocolate is lower calorie, the more expensive chocolate. So we want to, but of course the important thing is it's used for different processes. So like in ice cream, if you're going to take a Magnum or something, you're going to dip a Magnum into the chocolate, so it needs to flow very well. And then different chocolates. So the chocolate's not one thing. There's a whole range of chocolates with different fat contents, and so for different applications. And so we'd like to keep the cost low, but then if you put too much powder in, then the flow will be harder and it won't work. So that's why we have certain limits. So can we change this? I think that's an interesting thing. And we can look more recently and see that there's bad weather in West Africa. And so the cocoa harvests in West Africa have been disastrous. And so we can see from the start of this year, cocoa was trading at about $4,000 a ton, and it went up to over 12,000. And I did this at the start of July, but it's very erratic, but it's very high price, going up and down. And so this means that cocoa butter itself, it's trading at about $20,000 a ton, where it was, 6 to 8. So it's very, very expensive. You can expect increases in the price of chocolate, but so are there ways to avoid this? Of course, our work predates this. We wanted to see if we could control the solids content in chocolate and maybe reduce the cost of chocolate or give us different functionality in chocolate. So we went to the IFSTAR, which is the French Construction Institute. It's now Université Gustave Eiffel in Marne-la-Vallée. And so we worked with people working with concrete, because concrete is a very similar system to chocolate. So in concrete, you've got very expensive cement, and then you want to put lots of particles in, but it still needs to flow, and it still needs to have, the required strength. You don't want a catastrophic failure of your bridge or whatever. So it's the same kind of questions. And what we want to do, of course, is to pack our particles as well as we can into our chocolate. And so if we can pack them really well, we can get more solids in. We've still got the continuous cocoa butter phase, and so we can still get the flow we want. And so that's our idea. So we started off doing some work where we had a PhD student looking at what happens during chocolate. And how do we make chocolate? Well, we mix. This is dark. We're going to stick to dark chocolate because it's a bit simpler, but we're going to mix cocoa particles and sugar particles in with cocoa butter. You refine them, you put them through a mill, effectively, sort of a 5-roll refiner. You get small particles out the end, and then you conch them for several hours. So this is just a mixing phase. This drives off some of the bitter kind of flavors, but it also has some physical effects, and you add a bit of extra fat and maybe some emulsifier in this phase. So we wanted to see what was happening during the process, and so we can look at the average size of the particles. So clearly, you mix them, they're quite big, then you refine them. The particle size, when you refine it, the particle size goes down, but after that, the particle size isn't altered, but you do get changes in the particle size distribution. And so what effect does that have? So if we take samples at different process times during the processing, we can see, well, initially we've got lots of different size particles before we mill them, so it's the viscosity is very low. When you grind it, they're all the same size, so we get very high viscosity. And then during the mixing process, the viscosity decreases. Well, to here, then we add lecithin. It didn't seem to do so much difference. So this is what's happening during the chocolate making process. But what we want to look at is what's happening in the packing. And so we can see that throughout, so the packing's decreasing because we've got one size of particles here after the grinding, but then during the process, during the conching, the packing increases. So we can get better packing of our particles. Now this is just with taking one system and conching it. We can see what effects we can have on the packing. And if we look at the maximum packing throughout the process, we can see that it all fits with the theory. It all fits on, and this line gives us the kind of maximum we can expect based upon the particles we have. So what we want, based on the Krieger-Doherty equation. So what we want to do then is to control the packing by controlling the size of particles, but the particle size distribution, and then by doing that, we're able to get systems that work in the same way, but with a higher solids content. And if you're interested, we've published a paper explaining the theory behind the packing. And so we're able to get systems where we increase the packing of our particles. And by doing that, we're able to reduce the cost of chocolate, and And we've filed IP. You can read the IP if you're interested. Opportunities for improvement exist by increasing the packing fraction. So as well as the as this improved lower cost chocolate, perhaps we'll have a different network so we can reduce the amount of bloom. We'll have more cocoa in the system, so perhaps we get better tasting chocolate, and there's potential for improving, making better cocoa powder by pressing better, and different systems that if we can control the particle size distribution, control the packing, perhaps we can get various novelties. Okay, and so then just for my final example, we've seen, we discussed that the best chocolate in the world comes from Belgium, but I think we can also say the best fries in the world come from Belgium, so I have to talk about fries. Of course, the important thing with fries is to fry them twice, once at a low temperature to get you the nice soft interior, and then at a high temperature to give you the crusty surface. And then don't worry about the acrylamide that could be produced during that. So everyone loves fried food, and Cargill has a big oils business. We supply lots of food manufacturers and people making fries, companies like McCain, McDonald's, Burger King, and others. But oil's high in energy, isn't it? It's 900 calories for 100 grams, where sugar is 400. Sugar's high, but it's less. It's half of fat. So we don't want to leave oil in our foods. So the oils, why have we got the oil? Well, it's a heat transfer medium, isn't it? So we want to get the heat from into the fries as quickly as we can. When we're frying food, we're frying food so that we cook it as quickly as we can to try and keep it crispy, and keep the flavour of the food, rather than sort of boil it and have a much softer kind of option. So how can we reduce the amount of oil in our fries? Well, we want to understand the mechanisms of oil uptake, and in order to do that. So I think we need to remember that deep frying's a two-stage process. So we have the immersion stage, where the oil's in the fries in the fryer. What's happening is the water, it's boiling, isn't it? So the water's boiling, coming out of the fries. There's no oil going in. What we're doing is creating holes in the fry. Then we take it out, and then we've got a layer of oil on the surface, and we've created voids in the center, so it gets sucked in. So so after we've taken the fry out, we've got that layer of oil on the surface of the fry, and it's getting sucked in to the fry. So that's what we want to try and avoid. So if we can look at how oil uptake. Sorry, this was my colleagues. Look at the description of oil uptake. So it was only quite recently, relatively, that the people realised, oil's been replacing water. People thought oil replaced water during the frying, and then it was only in the 90s people realised it was coming at the last minute of immersion or after withdrawing the fry. And we've seen that it doesn't occur during immersion, but occurs after frying due to this under pressure sucking the oil in. And then also we think, well, you think of a fry, you've got potato cells. So it's where we've got damaged cells, of course, that there's room for the oil to come in. And the oil can only penetrate up to 3 cell layers. So it's not going to go deep into the surface, so into the fry, just into the outer edge. But that's enough to give us, quite a highly calorific product. So, and it occurs during the first minute of immersion of a fry. So it's important, to try and get the oil off as quickly as we can after frying. So here we have a multi-scale modeling of oil uptake, so we can see what's happening. If we look at the surface, we can look at the cells, we can look to see how the oil goes through. So we've developed a model, so we can look to see how the oil penetrates through the fry, and then how the oil saturation goes. And so you can see it's where there's a damaged cell, it's where we get the oil penetration. So the important thing is to keep your potato damage free, but of course you've cut it, so there will be some damage. So let's have a look at oil. When we pull it out of a surface, what happens? You see, well, we get these drips coming off, and you'll only ever see about 5 drips. So there's oil coming. This is just a glass rod, and so there's oil around the surface. And then when we pull it out, we'll only ever get about 5 drips coming off. So it's important to look at the coating, the way it drains, the dripping, and of course the heat transfer. Because as the heat comes out, maybe it'll start to crystallize. So we did this study to look at the looking at to predict the dripping and oil uptake of par-fried frozen French fries withdrawn vertically from hot frying oil. If you withdraw them vertically, you'll get better drainage, but of course that's not real life, is it? Because they're all in a basket, and then you shake the basket to try and get the oil off. But this is what we can start to look at. And so my colleagues looked at modeling of the oil coating, then modeling of the oil drainage and heat transfer, and it's relatively complex. So I won't go into the maths, but we can see, I mean, you integrate a few things, and substitute a few things, but we can look at, for impervious material, we can look to see how the drops come, and then we can take, so for a cylinder, these are how the mass of the droplets develop, and then this is where the droplets fall off. So we can see 1, 2, 3, 4, 5 droplets develop over the minute, and then they fall off at this time. And so this is actually what happens when you take a fry out. It's hard to get many droplets off the fry, and so we can look at the different sizes and things of the materials, and we can think about factors such as the roughness of the fries, and then we can compare, experiments with predictions, and so the prediction for a real French fry, and then the experimental value kind of fit close together. And if you're interested in any of the detail at all, then there's an article that's been written. So yes, so we can understand how oil interacts with the fry. We can see how the oil drains from the fry after we've fried it, and so now we can start to work on how we can optimize that. How can we make our oils better? Do we want the oil to stick better to the fry? Do we want to put lots of surfactants on? I doubt it. Or do we want to try and repel it from the fry somehow? So we decouple the different mechanisms. The evolution of the oil content, not as with time. Maintaining boiling for a couple of seconds, maintain the heat for seconds after we've removed it from the oil, can allow better dripping, and so that can allow frying. So perhaps you could look at designing your fryer somewhat better. So that's an interesting thing. I mean, that's not necessarily something we would be interested to do, but it could be useful to somebody. So the model can be used to evaluate the impact of product microstructure, geometry and process conditions on oil uptake. So I think I've come to the end of my talk. I hope I've shown you that that there's a wide variety of challenges in industrial research. Perhaps it's a bit different from academia, where we're perhaps working more as a team. There's cross-functional teams involved, and we saw that, with the sort of fermentation, material science, sensory science, teams involved, looking at that dessert. Research isn't the same as innovation, so we don't just want to understand how something's happening, how something's behaving. We're looking for an innovation. We're looking to create something. Successful innovation depends on teamwork, and this may involve researchers, marketeers, IP lawyers, operations managers, engineers, etc. Because, of course, we can come up with some good ideas in research, but if you can't make it, or our customers can't use it, then it's not going to be important. So networking is clearly going to be crucial. We need to maintain the connections with other colleagues, and so we need a developed within a company, a developed innovation ecosystem, and we need ideas. We can't have all the ideas ourselves. We need to be in a position where we get ideas from inside and outside of the organisation. And I think we saw with the work on chocolate that we developed with University Gustav Eiffel, that they don't need to be people working on food. There's lots of different ideas around which we can apply. And of course, the final thing, it's always nice to see your research in action. I think that's one of the benefits of industrial research. So I hope I've given you an introduction and then some summaries and some perspectives there. So thank you for your time.